anyway, here we go. Basically, we're going to talk about two different groups of carbohydrates or two different groups of sugar. We're going to talk about a type of carbohydrate that's called a simple carbohydrate, or we can call this simple sugars. And then we also have complex carbohydrates or complex sugars. Now, under simple carbohydrates, we're going to talk about two different groups. One is called a monosaccharide. Oops, that's a Z. And the second is called a disaccharide. I'll tell you what the heck these are. And then under complex, we're going to talk about polysaccharides. And we're going to talk about what kind of foods do we eat that are simple versus complex, and what is it doing to the body. Okay, so monosaccharides, these simple guys like glucose and fructose. And then disaccharides, you put two of them together, two monosaccharides, and you have a disaccharide, yeah? Okay. Now, you're going to have to remind me because I can't remember. Did we talk in here about what these do for us? What foods you get these from? Okay, so these are basically, if you think about what foods you get monosaccharides and disaccharides from, think of junk food. So cake, candy, cookies, that kind of thing. That, ice cream, we're getting usually monosaccharides and disaccharides. Now, of course, we can also get it from fruit, because fructose, okay, which, by the way, in our diet, fructose and fruit give us very similar results as eating a Snickers bar. So you eat a lot of fruit, it's like you're eating a lot of candy. You know, fruit is sort of nature's candy. Okay, eat a lot of honey, and that's another nature's candy. In the good old days, they basically made candy from honey. That's pretty much all you had. So when we're talking about these disaccharides and monosaccharides, we're talking about sweets, okay? When we get to polysaccharides, it's something like this. So polysaccharides are where you take these green things here. These are each glucose molecules. So you have a whole bunch of glucose molecules. Oh shoot, I'm sorry, mister. You have a whole bunch of glucose molecules that you can bond together, and you get this long kind of branching chain thing going on, and this is a polysaccharide, okay? Now, where do we get polysaccharides in the food that we eat? Well, we can get it from plants. We can also get it from animals. So if you eat meat, if you're a carnivore like me, okay, you can get it from animals too. So if the polysaccharide is found in an animal, we call this kind of polysaccharide glycogen. So when you eat meat, there are a few carbohydrates in the meat that you eat in the form of this polysaccharide. If it's from a plant, this is what we would call starch. And so plants that have a lot of starch would be like corn, potatoes, wheat. So like you're eating mashed potatoes, you're eating corn on the cob, you're eating pasta or bread, rice, are all made up of polysaccharides, all these glucose molecules. Now, one of the things that if you look at, you know, that food pyramid that everybody gets taught about, one of the things at the very bottom of that food pyramid are all the carbohydrates you're supposed to eat. And that the majority of your diet, 60% of the American diet, according to God Bless America, the United States government, is supposed to be made out of polysaccharides. So you should be eating 60% of your diet plant-based starch, potatoes, bread, rice, and so on. The problem with this is, once the United States government decided they were going to put that food pyramid out, which was in about the mid-1960s, see a direct increase with that food pyramid in the level of cancer and cardiovascular disease in the United States. Now, if you look at a country like Japan, okay, who they do eat rice, however, they also have a lot of fat in their diet as well, because they eat a lot of very fatty fish. And they don't eat nearly as much carbohydrates as a good old-fashioned, God bless America, American. They'll have a bowl of rice, and you and I, as Americans, will eat carbohydrates constantly from morning till night. We don't have a little carbohydrate for breakfast, a little carbohydrate for lunch, a little carbohydrate for dinner like they might in Japan, because they have their bowl of rice. We eat carbohydrates all the time, continuously. Matter of fact, the United States government tells us that we should be eating anywhere from 300 to 500 grams of carbohydrates a day. That's a lot of carbohydrates. If you were to look at countries that eat some carbohydrates at breakfast, lunch, and dinner, they eat 200 or less grams of carbohydrates a day. Their level of cardiovascular disease and cancer is extremely low compared to the levels in the United States. If you are more comfortable sitting over there.
Yeah, I am. Thank you.
Just grab a chair over there. You don't have to be in the middle of everybody. That's for me. So now let's look at what Americans did to Japan. We brought over Kentucky Fried Chicken. And we brought over McDonald's and Burger King and all those great places where when you think you're eating a hamburger, guess what? You're actually eating vegan when you go to Jack in the Box or McDonald's. Because 80 to 90% of that hamburger is actually made out of soybean. Did you know the U.S. government says that if you have at least 5% hamburger in the hamburger, even if 95% of it is made out of soybean, that's illegal for you to call it a hamburger? So when you go to McDonald's and you eat that hamburger, you're really kind of sort of eating a soy burger. And so soy is a complex carbohydrate. Has a lot of starch in it, a lot of this polysaccharide. So now we've increased the intake of carbohydrates in the Japanese people's diet because now they're eating fast food just like we do. And the rate of breast cancer and colon cancer and lung cancer and cardiovascular disease is now as high as it is in the United States. Now, how the heck did that happen? Because supposedly, according to the government, eating more carbohydrates and less fat in your diet will not make you fat, it'll make you skinny, and it'll make you much more healthy. However, here's another weird thing, which I don't quite understand, is that when that food pyramid thing came out, people got fatter. I have a son-in-law who is Irish, and he actually lives in Dublin, Ireland. And when he and my daughter come over to visit, he loves to bring his camera to the United States because he likes to take pictures of fat people. And the first time I saw him do this, he's actually got a fat person album. And he'll walk up to people, he's very polite about it, and he'll say to these people, "Could I take a picture of you?" And they're like, "Yeah, sure, no problem." And he'll tell them why. Because in Europe, they don't exist. And I'm like, yeah, okay, whatever. So we go over to visit, and we're in this little town in Ireland, and I said to him, I go, look over there. There's two very, very large people. And he goes, they're Americans. I'm like, no, they are not. He goes, yeah, they are. Irish people are not fat. So, of course, I have to go over there to see where they're from. Very nice, I'm smiling at them. Hi, where are you guys from? We're from New York. But, so why is it that, by the way, Ireland, where they eat more fat in their diet than you would ever dream of consuming in a day, are all skinny? Why is it you go to France, you don't find a single fat person there? Whereas all you got to do is walk out the door and you'll find plenty of Americans who are roly-polies. I mean, it's true. But supposedly we're eating this extremely healthy, good for you, United States American government-backed diet, what the heck is happening? And it's not so much that we might have extra fat on our body. That's not really it. What is really it is that we're so unhealthy. That's the really big deal. If you could be 500 pounds and feel great and be super healthy, nobody would care. But the whole idea is when we put extra weight on our body, we start to feel unhealthy too. Now, you can also have a lot of Americans who are downright skinny, and you start talking to these Americans and they're tired, and they don't feel good all the time. They have a hard time studying. They have a hard time thinking. These are skinny fat people. Because really what we're saying is it doesn't matter if you have extra weight on your body or you're super skinny. If you're sick inside, you're sick inside. Something's wrong. And the whole idea behind you taking this class is you want to learn how to make sure, not just you, okay, but how to make sure all those patients that you're going to see over the years are also more healthy. This is all about what your job is going to be. You want to work in the healthcare profession, you want to make sure people are healthy. And how do you make them healthy? Do you tell them to follow the government's diet? Or do you tell them to follow a more nutritious diet? And that's really the question you have to ask yourself. Is this United States government diet working for you? Are you happy so much that when you wake up in the morning you're like, oh, I am so ready to go and I am just happy to see the world and I've got all this energy and I can think great and I can stay up for 14 hours and just go, 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 go. And if you're not, well, are you on the right diet? Because it really affects how we feel about ourselves, how we are able to study, the energy level that we have. And then we know that sugar, one of the things, because that's what these are really a type of sugar. Even if it's sugar in a potato or sugar in bread, it's still sugar. And when it gets into your bloodstream, it actually destroys blood vessels. And it's the sugar that causes, remember we talked about the fact that your blood vessels are very smooth, they're very slick inside, and the sugar scrubs those blood vessels and causes things to stick to it. And now all of a sudden we have clogs in our arteries. If you're eating a low carbohydrate or a low sugar diet, your risk of having cardiovascular disease drops by over 90%. And the majority of Americans will die from cardiovascular disease. So this year, 90% of the Americans who die will die due to cardiovascular disease. So if you could decrease your risk of cardiovascular disease, you would live a lot longer. I was watching this lady on the news, she's 103 years old, and they asked her, so how is it that you got to be 103 years old? And she looked at the guy like he was stupid. And she said to him, it's because I eat bacon every morning. Now, that might sound crazy, but it makes a lot of sense. Because here's the other thing we're going to talk about. We're going to talk about fats next. And I want you to know this. This is a term we use in chemistry. Like dissolves like. So when somebody tells you that you have fat clogging your arteries, how the heck are you going to get it out of your arteries? Well, here's what they tell you. To get the fat out of your arteries, eat less fat. That's absolutely 100% wrong. Because I could also write it like this. Fat dissolves fat. So the only reason that this fat, this cholesterol, is clogging the artery is because we had to take that really smooth, slick artery and we had to mess up the inside. We talked about this, right? Where sugar scours your arteries on the inside, and now it's not so slick anymore, and things like cholesterol and fat can stick. So if I want to clean out my arteries and get rid of the clogs, here's what my cardiovascular surgeon is going to tell me to do. Take fish oil pills. That's what he'll tell me to do. Now, how is that possible? Because, okay, when we talk about fats, all right, turn the picture here. When we talk about fats, that's not what I want. I want this. Fats can be called lipids. Okay? And there's a couple different types of fats. And we're told that these fats are bad for us, and you might have heard of this before. There's a type of fat called a saturated fat. And then there's another type of fat called an unsaturated fat. And then there's another type of fat called a trans fat. Okay? So, somebody tell me which of these fats are supposed to be super good for us according to God Bless America, our government? Unsaturated. Exactly. But now I'm telling you, this is the truth. If I got clogs in my arteries and I go to a cardiovascular surgeon, that cardiovascular surgeon is going to tell me to pop fish oil pills. Because that cardiovascular surgeon knows that fat dissolves fat. So he wants me to pop these fish oil pills to help to dissolve the fat out of my arteries. Now, what kind of fat are fish oil pills, do you think? Saturated, unsaturated, or trans fats? Because, like, this is a doctor. What would they tell me? Why would they tell me to take saturated fat to unclog my arteries when saturated fat supposedly clogged my arteries? Yeah, that's exactly right. And did the fat actually start the clogging of my arteries? No, it's absolutely the sugar that started the clogging. So if I want to unclog them, I have to first dissolve the fat out of my arteries, and then I have to heal the walls of my arteries. How would you recommend I heal the walls of my arteries?
Cheerios.
Cheerios! Oh, a high complex carbohydrate, sugar, polysaccharide Cheerios. Would this be, according to my cardiovascular surgeon, is this truly the way to heal the walls of my arteries?
No.
Hell no, I shouldn't say that. But yes, you're right, I emphatically agree with that. Because here's the problem. That's exactly what they'll tell me to do. They'll tell me to take fish oil pills and eat Cheerios. There's something really wrong with this. Because now I'm eating a lot of complex carbohydrates, which will ruin the walls of my arteries more, and now I have all the saturated fat I'm taking in the fish oil pills, which will clog my arteries more. So what do I need to do to unclog the artery and heal the wall? I gotta eat more saturated fat and eat less carbohydrates. So instead of doing what the government says, you should be eating below 200 grams of carbs per day. And by the way, if you want to lose weight, you should be eating about 20 grams per day. Now here's the problem. Look at the food labels of some of the foods that you are eating on a daily basis. And I'm going to guess many of you are anywhere between 5 to 1,000 grams of carbs per day. You are right on your way to cardiovascular disease. You're doing exactly what the government would say you should be doing. Lots of carbohydrates ruining the inside of your arteries. Matter of fact, they did a study not too long ago on men who were coming back from Iraq and Iran and Afghanistan who were in the military, and these unfortunate military people had died. And they were looking at military people between the ages of 18 and 21. And what they were able to show is that over 80% of them already had massive clogging in their arteries at the age of 18. That's scary when you're talking about being 18 years old. You shouldn't have any clogs in your arteries at 18. So how is this happening? Well, they're eating a lot of Cheerios. And they're putting sugar on those Cheerios. And then on top of it, they're eating a lot of fat as well. So when you're talking to your patients, and by the way, I realize the majority of you aren't going to change your diet, and I am not here to make you change your diet. I don't really care what your diet is. It doesn't affect me at all what your diet is. But here's what's important. Whether you abide by it or not, you need to know what's healthy for your patient. Because you're going to be responsible for helping your patient to be more healthy. I know how it is, you know. People who mow somebody's lawn for a living, they're landscapers or whatever, they go out, they do a beautiful job landscaping somebody else's lawn. They're too tired to come home and landscape their own lawn. It looks like crap. Okay? When you work in the health profession, you will help all kinds of other people, but take care of yourself? Probably not. Okay? I get it. So I'm not preaching to you. I'm just telling you what the scientific facts say. And the scientific facts say that we should be eating more fat and less carbohydrates. And you shouldn't really be eating very many carbohydrates at all. And 200 grams of carbohydrates in a day really is no amount of carbohydrates at all. Look at how many grams of carbs are in a tall caramel frappuccino from Starbucks. Did I guess it right? Okay, there's about 150 grams. Yeah, there's about between 50 to 60 grams of carbohydrates in a single slice of bread. What about beer? It's all carbohydrates. So there's as many carbohydrates in a glass of beer as in a frappuccino. Probably would too. Now, fats. When we look at something that's a saturated versus an unsaturated fat, saturated fats usually from animals. So you know that bacon that lady was eating every morning to get to 103? She's eating saturated fat for breakfast. Now, if you're not sure if something's a saturated fat or not, you're not sure if it came from an animal or not, also usually it's a solid at room temperature. So if you're talking about butter, this would be a saturated fat because it's a solid at room temperature. Now, by the way, margarine. What's the #1 ingredient in margarine? Plastic.
Swear.
The #1 ingredient in margarine is plastic. Because what they do is they melt down the plastic, turn it into an oil, and then use that oil to make margarine. So during World War II, there just wasn't enough food for everybody to go around. And so we needed to send some of the better stuff to the guys overseas who were fighting during World War II. So this is really when the government started making that food pyramid. And they started sending the butter and the milk and the eggs and the meat and all that really fatty stuff over to the military guys to give them the energy to keep them going. So what they told us here is, oh no, fats are bad for you. So you should eat all this other stuff that the military guys, they didn't want to eat all that. They wanted a good piece of steak and butter and all that kind of stuff because, you know, they were working hard. And so there wasn't enough butter, there wasn't enough milk, so they developed margarine. It's 100% artificial. There's nothing natural about it at all. And now I can't believe it's not butter. Yeah, it's not butter. It's not anything you probably should be eating because it's made of mostly plastic, which is just really scary. Now, if we're talking about saturated fats, these are mainly the oils that you can think of, okay? And this is going to be vegetable. And it's going to be liquid at room temperature. Now here's the problem. Here's where the unsaturated fat comes in and potentially is really bad for you. Because a lot of these vegetable oils like corn oil and canola oil and grapeseed oil, these are all coming from plants that if you were to take those plants and squish them, you couldn't get any oil out of them. Whereas like with olive oil, if you take olive oil and squish it, you can get oil out of it. It naturally has an oily substance in it. corn, I don't care how much you squish corn, you're not going to get oil out of corn. You take grape seeds, you squish them, you're not going to get oil out of this. So what we have to do to get oil out of corn or soybean or grape seeds is we have to put it through these multiple chemical processes to turn it into oil. And when they started doing things like that, they found that if you took this canola oil or cottonseed or corn oil and you cooked it, you raised it to a temperature to like, cook your French fries in. When you got it heated up, it became unstable and it changed shape. And instead of having the shape of what we call a trans fat, it now, of an unsaturated fat, it now turned into a different shape, which is what we call a trans fat. So corn oil, canola oil, any of those oils except for like olive oil or coconut oil, they don't, not coconut, strike that, olive oil, they don't squish, they don't make an oil. When I heat them up, they become a trans fat. And nobody will disagree with this, that trans fats are what we call carcinogenic. That means they cause cancer. So once upon a time, places like McDonald's used to fry their French fries in beef fat. So fat that would come from a cow. And people were like, oh, that's gross. You kill cows and you make fat and fry French fries and that's disgusting. And you shouldn't do that. It was okay to eat the hamburger that had cow in it, but just don't eat the cow's fat to cook the French fries in. It's just disgusting, so you need to change this. And so McDonald's goes, okay, if you want us to change, how about we use soybean oil? Okay. So they picked a vegetable oil, and it's very cheap and inexpensive. McDonald's can make a lot of profit using it. But the problem is, when you cook French fries in beef fat at high temperature does not become a trans fat. It is not carcinogenic. But if you cook soybean oil at a high temperature, it becomes a trans fat. And now those French fries you get from McDonald's, In-N-Out, Burger King, wherever, now they're cancer causing. So you take your kid to McDonald's and you get them that Happy Meal and a little colon cancer on the side.
Is it the same with like olive oils and corn oils?
Yes, not olive oil. Olive oil is a natural saturated fat where if I press olives, the oil comes out. I don't have to put it through any kind of chemical process. It will not become a trans fat. But if I have to put a soybean through chemical processes, which I do, to make oil out of it, if I heat it up, it will become a trans fat.
Is coconut oil a trans fat when it's heated up?
No.
Okay.
Coconut oil is a saturated fat. It's one of the few saturated fats that are vegetables.
So lard is good then?
Yes. Lard is pig fat. Tallow is beef fat. Is that healthy for you? Yes. Yes, I am, aren't I? I'm saying eat more bacon. Less Cheerios.
So it's better to cook your chicken in olive oil than everything.
No, it's better to cook your chicken in butter. Slap the butter in there, baby. Make it taste good. Cook that ribeye steak in tons of butter. You want to lose weight? Cook your ribeye steak in butter. Not olive oil. Maybe even cook it in coconut oil because it's even higher in saturated fat. But here's what you have to do. You have to raise your fat level and lower your carbohydrate level. If you keep your carbohydrate level up and raise your fat level, here's the problem. You will get fatter. And you will have more cardiovascular disease. And it will kill you faster. If you're going to change your diet, you have to lower the carbohydrate level. I can't talk while other people are talking. It takes my importance away. You have to lower your carbohydrate level, that's important, and then you raise your fat. You can't keep them both up. And I've had students who have come back to me and go, oh my gosh, Dr. Harvey, I gained like 25 pounds on this crazy diet. And I'm like, oh yeah, you did not lower your carb level at all, did you? Well, no, I just like raised my fat. You can't do that. There's a ratio. Eat all the fat you want, but make sure your carbs are below 200 grams. And if you really want to lose weight, get them down to 50 or 20. By the way, here's another thing, this diet that I'm telling you about. If you know somebody who has an autoimmune disease like multiple sclerosis or lupus, this is an autoimmune disease diet. It also takes down inflammation. I've known several people who have had multiple sclerosis, were in wheelchairs, went on this diet, and are walking again. Even one of them ran a marathon. So what this does is it allows your immune system to become more healthy as well. It gives you more energy because where we get most of our energy from are from lipids or from fats. So for instance, carbohydrates. When does our body use carbohydrates as energy? Well, whenever you need quick energy. So for instance, somebody comes in this classroom and screams, "Fire!" and we all go running out the door, you're burning carbohydrates. Or you're at the gym and you're bicycling away, you're burning carbohydrates. You're not even burning fat. As you do this moving, your body uses carbohydrates. The rest of the day, you burn fat. Now, why is exercise good for you? Well, let's say I exercise for 10 minutes. That's it. I'm not going to exercise for any more than 10 minutes in a day. What that does is it actually allows my whole body, my metabolism, to kind of rev up a bit. And I will burn fat faster for about an hour after my 10 minutes. If I exercise for 20 minutes, or even let's say I exercise for 30 minutes in a day, I could do 10 minutes in the morning, 10 minutes in the afternoon, 10 minutes in the evening. It doesn't have to be all in one block. Every 10 minutes I exercise, it speeds my metabolism up for about an hour. So if I want to burn fat faster, I exercise for 30 minutes in a day, I will burn fat 3 hours at a faster rate than I normally would if I just sat around. But while you're sitting around right now, as long as you're not eating anything, you're burning fat. When you go to sleep, you burn fat. I don't know if you've ever done this. You step on a scale before you go to bed, step on a scale the next morning, you're about 2 pounds skinnier. Okay? You burn fat overnight. You lost weight. I actually heard of a guy who somebody told him you burn fat while you're asleep, so he decided to just keep taking sleeping pills. That was his diet. Now, unfortunately, that's really unhealthy for you. He ended up dying from this because all he was doing was for almost 30 days just sleeping. That's bad for your body. Do not take any sleeping pills since I tell you you burn fat while you're asleep, okay? Not good. But fat burns at a much longer, lower rate when we're more calm. The quick energy is all about carbohydrates. And how many times a day do you do quick energy? I'm going to guess not often. And so if you don't do it very often, you don't need as many carbs. You don't require as much. Any questions so far about this weird information I'm telling you? Just saying. Yeah.
What kind of fat would peanut butter be?
Peanut butter is a saturated fat. Super good for you. Probably. Good idea. Buy yourself some coconut oil.
Could you like fast to get into a diet like that?
Could you fast to get into a diet like that? Absolutely, positively, don't even try that. That's crazy. Because here's what happens. You know, our body is so used to all these carbs. And let's say you're eating 500 grams of carbs a day, and I'm telling you to get to 200. You do not want to go from today to tomorrow down to 200 grams. You're going to be sick. You are going to get seriously sick. You cut it down slowly, very slowly. And when you get to 200 grams and you want to lose weight, okay, you have to cut it down even more. And sometimes this could take 3-6 months for a person to get down to maybe 50 or 20 grams of carbs. Now, by the way, children can eat this diet too, but they should not eat any less than 100 grams of carbs a day, ever. They should never get down to 50 or 20. It's not healthy for them. They need a little bit more carbs than you would need. Geriatric patients, so you're talking people who are 60, 70, 80 years old, they should be eating about 100 grams of carbs or more a day. So never any less than 200 grams, even if they're trying to lose weight. Their body believe it or not, is very much like your 2-year-old's body. And so things are very different than people your age would be. But yeah, you never want to try to fast your way into this and get there overnight. It's very bad. You have to slowly convert your engine. You're doing a slow engine conversion. This is very, very slow going. Any other questions? A couple other things I want you to know. Fat is also very important for our body because it's there for insulation as far as helping us to maintain heat. Okay? If you know people who are super duper skinny, usually they're also very cold, and that's because they don't have enough fat on their body. Fat holds heat, and that's very important. We also have a lot of fat around our major organs, like our heart has a lot of fat around it. Our kidneys, lots and lots of fat. It's helping for insulation, like if you're moving around, your heart hits your ribs or whatever, helps to insulate it, but they also need a lot of energy. So you want a lot of fat right there for the heart to consume, because you know it's beating and moving all day long. It has to have a really good energy supply. All right, so we're going to start talking about another type of fat that is found in the body, except for this isn't the kind of fat you usually think about when we pack a little too much on the hips or, you know, under the double chin or whatever. This is a type of fat called a phospholipid. Now, if you look at the phospholipid, it's kind of weird. It has this one portion up here made out of these kind of chemicals. Can't see it too well, and I'm not asking you to know these or anything. And then there's these two long chains of carbon. So some people said when they look at the phospholipid, I don't know how they got this, but somebody looked at it and said, oh, that kind of looks like a tadpole. Okay, whatever. And so they call this chemical part the head, and this part down here, saying it had like 2 tails. Okay? So the chemical part, the head, if you look real close, although you can't really see it in there, there's a chemical that has a positive charge, and then there's another chemical that has a negative charge. Because it has this positive and negative charge, this portion of this chemical, we're able to say is polar. Now remember the saying, like dissolves in like. Something that has a positive and negative to it is what we call polar. Water, we haven't really talked about this, but water, if you look at a water molecule, okay, we know water is H2O, right? And water really kind of looks like this. And this oxygen, okay, you'll learn this in chemistry more, but this oxygen is kind of sort of negative charge. And these hydrogens are kind of sort of slightly positive charge. So anything that has a charge on it, positive charge, negative charge, or a positive and a negative charge, we'd say it's polar. And if like dissolves in like, if I tell you that salt, sodium chloride, it has a positive and a negative charge on it, would you guess this can dissolve in water? Because it's got a positive and negative charge. Water has a positive and negative charge. Anything that has a charge on it can dissolve in water. So what if I tell you sugar? Well, let's not do that. Let's not confuse things. What if I tell you that I have a chemical like this, which is a phosphate, and it has a negative charge on it? Would you guess it can or cannot dissolve in water? What would you guess? Can? Why? Because it's polar. Because anything that has a positive or a negative charge on it would be considered a type of polar molecule. And if it's polar and water is polar and like dissolves in like, it can dissolve in water. Now what if I tell you that a saturated fat like coconut oil does not have a charge on it? Can it dissolve in water? No. And you know that. If you took a glass of water and you put some olive oil in water, does the olive oil dissolve in water? No. Fat is not polar. Matter of fact, we say fat is non-polar. portion of our phospholipid has a positive and a negative charge. These tails of the phospholipid are actually made out of fat, which means that they are non-polar. So phospholipids are kind of weird. They have a polar part and they have a non-polar part to it. Most molecules are either polar or they're non-polar, they're not both. This one happens to be both polar and non-polar. Now there's a really good reason for this, because phospholipids make up the membrane surrounding our cell. So this membrane here, what we call the cell membrane, this is made up of phospholipids. Now, okay, watch this. Out here on the outside of our cell, we have what's called the extracellular fluid, which by the way is mostly water. Inside of our cell, mostly what's inside of our cell is water, and since it's inside, we call this the intracellular fluid. Now what if I said that I have a cell membrane that is made up of a chemical that is purely polar? Okay, now watch. So my cell membrane, I'm going to say this is 100% polar. And the outside of the cell is surrounded by water, and the inside of the cell is made up of mostly water. What will happen to my cell membrane? It'll dissolve. That's exactly right. Because polar dissolves in polar. And if my cell membrane is polar and water is polar, my cell membrane will dissolve in polar. Would you guess that your cell membranes are made out of a chemical that's polar? No, because you'd be a puddle of water on the floor. You have to be made out of something else. Okay, now what if instead I tell you that my cell membrane is made out of a substance that is non-polar? Okay, like fat. So now think about, I have a glass of water, and I'm going to pour some olive oil in that water, and I'm going to put a lid on my glass of water, and I'm going to shake. What happens to the olive oil when I shake that glass of water? Come on, y'all have done this at least once in your life. What does it do? It breaks up, right? It totally breaks apart. So what if I tell you that my cell membranes are made up of a substance that's non-polar, like olive oil, and I start waving at you? What's going to happen to all my cell membranes? They're going to break up, right? And my hand's going to fly off and like hit her in the face. I mean, literally, that is exactly what would happen. Because you can't have a cell membrane, first of all, that's going to dissolve in water. That would really suck. Okay? And you can't have a cell membrane that's made out of fat so that when we move, it breaks up and parts fall off. That would be just strange. Okay? So instead, we have a cell membrane that is made out of a chemical that's part polar and part non-polar. Because the polar part is attached to the non-polar, it can't dissolve anymore. And because the non-polar is attached to the polar, it can't separate. So if you look at the cell membrane, okay, it's set up like this. These are all our polar heads, and they're all really tightly packed next to each other, super tightly packed. And then here are all our non-polar tails coming off, making up our cell membrane. So out here, this is the extracellular fluid, and here, this is the intracellular fluid. Now there's a problem, because if water can squeeze up in between these guys, it can separate the membrane, and your arm falls off. So the way this is situated is you have two layers of phospholipids. The polar heads are always by the water portion, the extracellular fluid or the intracellular fluid. And they're so tight together that if water tries to get up in between one of them? It can't. So it can't separate your membrane like shaking olive oil in a glass. It can't separate your membrane. Your arm's not going to fall off. And so you have what we call a phospholipid bilayer. And this is what makes up your cell membrane. So it looks like this. Here's the inside of the cell, the intracellular fluid, and here's the outside of the cell, what we call the extracellular fluid, and all the polar heads are pointed towards the inside or the outside. All the non-polar tails are sandwiched in the middle. Any questions? I know you all got it perfectly, right? Okay. There is another kind of chemical found in the human body that we also can make from fat. These chemicals are called steroids. Now, steroids fall into a group called hormones. So we have two types of hormones. We have steroid hormones, and then we have another group of hormones called protein hormones. Steroid hormones come from a type of fat called cholesterol. And of course, protein hormones, I bet you couldn't guess what they're from. That would be like protein. Okay, now let me just back up a second and ask you this question. Any idea what a hormone is? No idea whatsoever?
Like tell your body what to do.
Tell your body what to do. That is a pretty good explanation. It's a chemical that can tell your body what to do. But there's a couple very important rules on whether this chemical can be a hormone or not. So number one, if a chemical is going to be a hormone, it has to float through your bloodstream. So it's got to have floated through your bloodstream. And then it has to be made at point A, float through your bloodstream, go to point B, and tell that area of your body what to do. If it doesn't go from point A through the bloodstream to point B, not a hormone. So it has to travel through the body, and the way it travels is it has to do it through the blood. And then it'll tell your body what to do. It tells it, hey, look, I want you to make this chemical, or I want you to stop doing this. And sometimes you'll hear people say it's a chemical messenger, but it has to have moved through your bloodstream, and it has to have traveled through the body. So if steroid hormones are made out of fat, can they dissolve in water? What? No? Why? You're right. You're correct. Why? They're nonpolar. Can nonpolar things dissolve in water? What kind of things can dissolve in water?
Polar.
Oh, you're getting it. That's wonderful. Now, by the way, some kinds of steroid hormones that we make in our body you've heard of before. Things like testosterone and estrogen. Maybe you've even heard of things like progesterone, or maybe cortisol, or DHEA. These are all types of steroid hormones. We'll talk a little bit later about what the heck they do. But notice, okay, this molecule right here, this is cholesterol. And cholesterol can be turned into estrogen. Or cholesterol can be turned into testosterone. Very similar in structure. Now, by the way, something else that your body can do. Let's say that we have a patient who has been told by their doctor, do not eat anything that has cholesterol in it. What is the doctor actually telling the patient not to eat? Maybe. What kind of food, I should ask? What kind of food is the doctor telling the patient not to eat?
Well, I was going to say bad cholesterol because there's good cholesterol too, right?
Yeah, but doctors don't care about that. They just say don't eat any cholesterol. Chicken? Ah, yes, that would be, chicken has cholesterol. Say it again?
Salt.
Nope. You can't get cholesterol from salt.
What, egg?
Eggs? Yes.
Butter. Saturated.
Butter.
So dairy saturated fat.
Saturated fats. Animal products. So eggs, butter from cows, chicken, they're all going to come from animal products. We get cholesterol from animal products. Now look, really what's happening is we eat saturated fat and our body can turn this into cholesterol. Well, holy cow, maybe we shouldn't be eating saturated fat. Because isn't cholesterol evil? Well, no, it really isn't. You have to make steroid hormones with cholesterol, and there's a whole bunch of other things your body has to have cholesterol for. And cholesterol will not stick to the walls of your arteries unless something happens first. What is that something? You got to scratch it. You've got to damage it with what?
Sugar.
Sugar. So if I'm not eating so much sugar, even if I'm eating a steak, then is it going to damage my arteries? No, it's not. And the problem for us is if we cut too much saturated fat out of our diet, we can't make enough cholesterol, which then means we can't make enough steroid hormones. So what happens to a man who cuts so much animal product out of his diet? He doesn't produce as much testosterone. It's probably not a good idea, gentlemen. I just could think of a whole bunch of reasons why you wouldn't want your testosterone levels to go down, but we won't go there yet. We'll talk about that in the reproductive part. Okay, the next kind of molecule we need to talk about are proteins. Okay? So these are very important, obviously, to the body. You've got to have proteins, and you have to have them in your diet. So there's two different groups of proteins. There's a group of proteins we call structural proteins. And there are a group of proteins called functional proteins. So these are the two main groups of proteins in our body, structural proteins and functional proteins. Now structural proteins, these can be found in like our hair, our bones, what's called connective tissue. I'll show you connective tissue later, but it's basically things that hold all our organs together. It holds our skin onto our body. It connects things, okay? Another thing is of structural proteins, what else? Oh, like fingernails. These are structural proteins. Now, functional proteins would be like heart muscle, skeletal muscle. So basically our muscles are functional proteins. Those protein hormones that I just mentioned a minute ago. These are functional proteins. Things like antibodies. Our immune system makes antibodies, and antibodies are things that help to kill off bacteria in our system, so we'll talk about those later too. So antibodies.
Is hemoglobin a functional?
Yeah. Enzymes, we'll talk about that today, and then we'll put hemoglobin down. Hemoglobin is inside our red blood cells. It helps us to carry oxygen. These are all examples of functional proteins. So proteins in our body are made up of these chemicals called amino acids. Now you may have heard of this before. And in the human body, proteins are really, really big molecules. So for instance, the smallest protein we have in the human body is like 1,500 amino acids long. The biggest protein we have in the human body is like 50,000 amino acids long. So proteins are pretty dang big molecules. And we have 20 different types of amino acids that are necessary to make up our proteins. And every single protein has to have all 20 different types of amino acids in it, which means you have to be able to eat those 20 different types of amino acids in your diet in order for you to be able to make protein. So think about this, okay, your heart, it's beating every day, and it's made up of mostly protein. And as your heart beats, some of those proteins fall apart. It's no big deal, because as long as you're eating correctly, you have all the amino acids necessary to build those proteins back up, build your heart back up. It keeps functioning. But let me tell you a story. In around 1965, there was a company that came out that said that they had this protein powder that would make you skinny. So lots and lots of people bought it, and what you had to do is you took a scoop of this protein powder and you put it in water. And you drank this protein powder for breakfast, lunch, and dinner and ate nothing else. And I'm thinking, no duh, you would become skinny, okay? But there was a problem. About 6 months after this protein powder came on the market, there were hundreds of people across the United States dying of heart attacks. Now, imagine all you're eating all day long, breakfast, lunch, and dinner, is this protein powder. And then imagine if I tell you that, oops, this company only put 19 of the 20 amino acids you need every day to build proteins in that protein powder. How come these people had heart attacks?
Missed one. They're hitting instead of 20.
They missed one. If I am breaking down protein in my heart and I only have 19 out of the 20 necessary amino acids to build a protein, I can't build any. I have to have all 20 of those amino acids in order to build a protein. And so these people had 19 out of 20. They couldn't build a single protein. So every day their heart started to lose some of its protein, but they couldn't build it back up. And after about 6 months, they would die of a heart attack. Not good. So it's very important that we have these 20 amino acids in our diet. Now, the reason I tell you about this is because if you're a carnivore like me, you get 20 amino acids in your diet every day, because when you eat meat, meat is protein, and that protein has all 20 amino acids in it. But if you're a vegetarian, you don't necessarily get all 20 amino acids in your diet every day. As a matter of fact, if your patients are going to become a vegetarian, it's very important for you to tell them they need to study how to do it correctly. Or maybe they need to see a nutritionist to help them learn how to do it correctly. Because they have to eat certain combinations of food every day in order to get all 20 amino acids in their diet. So for instance, if they eat peanut butter on wheat bread, they'll get all 20 amino acids. Or if they eat red beans and rice, they'll get all 20 amino acids. So there's certain combinations you have to eat as a vegetarian every day in order to be able to build your proteins correctly. And I don't know if you know anybody who's a vegetarian, but if they're not doing it correctly, you can tell. You can tell that they don't look exactly healthy, and they usually don't have a lot of muscle mass, and they have a lot of problems. So it's very important for you to tell them they have to know how to be this vegetarian correctly, or just eat meat. Now, here's some examples of the amino acids, and I want to show you in this picture right here. You have what's called an amine group, and this C double bond OOH, this is an acid group, and that's why we call this an amino acid. We have the amine and we have the acid. And every single one of the 20 amino acids has an amine and an acid, an amine and an acid. What makes them different is this green group right here. And you'll hear people refer to this as an R group, or they'll refer to this as a functional group. So here's a great test question. Which group makes amino acids different from each other? The R group or functional group. Very good. So in glycine, one of the amino acids, hydrogen, is the functional group. In aspartic acid, it would be a methyl and a carboxylic acid. Or in cysteine, you have a methyl and a sulfur. So in all 20 amino acids, this R or this functional group is different from each other. But we still have all the amine and the acid group, keeping them the same. Now, if we bond these amino acids together, we're going to form what's called a peptide bond. So put two amino acids together, you've made a peptide bond. If I have 50,000 amino acids that I bond together, I got a heck of a lot of peptide bonds, don't I? So this is why you'll also hear people call a protein a polypeptide, because poly means many. This is a chemical that has many peptide bonds. So the word polypeptide is the same thing as protein. You can say something is a protein, or you can say something is a polypeptide. It means exactly the same thing. So a peptide bond is the bond that joins two amino acids together. And a protein, which has a lot of peptide bonds, is what we call a polypeptide. More of those flashcards I'm sure all of you are making, right? Great words on those flashcards. By the way, next Tuesday, you are going to have your first quiz, so be prepared. It's everything that we've lectured on so far. It's going to be on your first quiz, okay? So you have your clickers on your iPhone or your other Androids and everything, yes? You got the app? Excellent. We're going to have that quiz first thing when we come into class on Tuesday. And then we will be having a quiz every Tuesday after that. So these are two amino acids. We're bonding them together. We got ourselves a peptide bond right here. Now, if I take amino acids and I start bonding them together, so I get all these amino acids, whoops, hello. I get 50,000 of them that I bonded together. Eventually, I'm going to get this really long chain of amino acids, right? This super long chain, which would look something like this. All these little beads would represent amino acids. And I'd have this long chain of amino acids. That long chain of amino acids is called a primary structure. So what we're doing is we're taking all these amino acids and we're bonding them together. Okay? So we're getting these, we're bonding a whole bunch together. Now notice we've got hydrogens here, hydrogens here, hydrogens down here, hydrogens over here, hydrogens way up here. So what you have is you have hydrogens in this long chain coming out the top. You've got some coming out towards you. Got some coming out towards me, some coming out the bottom. And then you also have things like oxygens and carbons that are sticking out in 3-dimension from this long chain. And those hydrogens love to bond to things like oxygens and carbons. And so if you have them sticking out in 3D, they'll start bonding to each other. And eventually you'll see the long chain take on a shape something like this. It'll become like this kind of twisted, sort of like a ladder type of shape. And when you get this twisted ladder type of shape, this is what we refer to as a secondary structure. So it's all these hydrogens bonding to each other that makes our long chain take on this twisted type of shape. This is a secondary structure of protein. So you get a bunch of hydrogens bonding with each other, and that long strand turns into a twisted ladder, or what we would call an alpha helix. Now sometimes, once you form this alpha helix, some of the hydrogens will continue to bond. And then you'll see like the end of it fold inward, or the other end fold inward, so that you get something like this. Look at this kind of folding, sort of weird looking thing. And this is the ends of this twisted ladder just kind of folding in on itself over and over again, so that you get this twisted looking thing here, which is a tertiary structure. So we're going to have more hydrogen bonds forming, so this protein just kind of folds in on itself. And by the way, not only sometimes do you call it a tertiary structure, but you'll hear some people call it a glob of protein. Just sort of looks like some mess, some glob that got all put together. But again, this is because we have all these hydrogens that are bonding with things, causing this folding in on itself, or creating this glob of protein. If you take 4 globs of protein, which is what we have in this picture in the bottom here, if you take 4 globs of protein and you bind them together, you have what's called a quaternary structure. So you take 4 globs of protein, you bond them all together, you get a quaternary structure. Any proteins that are primary or secondary structure, these are all structural proteins. So your hair is a secondary protein. The connective tissue in your skin is a primary structure protein. So primary, the long chain, or secondary, the alpha helix, those are all structural proteins. Tertiary proteins, which are the globs, These are all functional proteins except hemoglobin. Hemoglobin is the only quaternary structure we have. So enzymes, antibodies, protein hormones, all those are tertiary. They're globs. Hemoglobin is the only quaternary structure, the 4 globs together. That's hemoglobin, which again is a chemical in our red blood cells, which we'll talk about a little bit later. Any questions? So, proteins can change shape. They have the ability to be like a transformer. 1 minute they're protein, the next minute they're a robot. I don't know. Anyway, but they can change shape. Now, sometimes people will say they change conformation, or sometimes they'll say they change configuration, but those are just fancy words for they change shape. So let's talk about how they change shape, and then we'll talk about the fact that sometimes they can change shape so much that they're no good anymore. So, I can have a protein, let's say it's a glob, this weird, funky looking, folded in on itself, just sort of a glob of protein. And I can get that protein to change shape. And then I can get that protein to go back to its original shape. And get it to change shape and go back and change shape and go back. Well, why the heck do I want proteins that can change shape? Well, sometimes when they're in one shape, the protein is off, not doing anything, taking a siesta, and then I change it to a different shape, and now all of a sudden it's on, and it's doing something in the body. And then I can turn it back off by putting it in its original shape. So sometimes when I change the shape of proteins, it turns them on, turns them off. Sometimes when I change the shape of proteins, I can make them do one job in one shape and a different job in another shape. Now, how do I change the shape of proteins? Well, remember, I got that shape by all these hydrogens bonding with stuff. In one shape, I have all the hydrogens bonding. If I make those hydrogens break some of their bonds, not all of them, but some of them, I can get a shape change. Now I make all those hydrogens form their bonds again, I go back to the original shape. Break some hydrogen bonds, I get a shape change. Form the hydrogen bonds again, I go back to the original shape. So to change the shape of a protein, I get a few, not all, a few hydrogen bonds breaking, I get a shape change. Make those hydrogen bonds reform again, I go back to the original shape. So I can get proteins to do different jobs in my body. Like for instance, when your heart beats, guess what? Those are proteins changing shape, going back to their original shape. Changing shape, back to their original. Changing shape, back to their original. Hydrogen bonds break, your heart contracts. Hydrogen bonds form, your muscle relaxes. How do you think moving your muscle is working? You're doing shape changes. And a lot of this has to do with hydrogen bonds breaking or forming. So we need these proteins in the body to be able to change configuration or change shape. And that's all about hydrogen bonds breaking and reforming. But sometimes there are instances in our body where things go wrong, we get sick, bad stuff happens, and it can affect our proteins. And when it does, it can make way too many hydrogen bonds break. Too many. So that instead of our protein just changing shape a little bit, it will change shape so much, it totally falls apart. When too many hydrogen bonds break and our protein totally disintegrates, falls apart, we say that that protein has denatured. This is where our protein loses its shape, can't perform its function anymore. That's what we do when we denature a protein. Now there's two major ways to denature proteins. change the pH. So if we drop the pH in the human body, make the pH go down, have we become acidic or basic if the pH goes down? Do you agree with him? Do we become more acidic if the pH goes down?
Yeah.
Yes, we do. Some of you shook your head no. Go back and study your pH scale again. So if the pH goes down, we become more acidic. And here's the problem. Usually when we become more acidic is because we're really sick and we build up all these waste products that are very acidic in our body. It makes our pH go down, and when our pH drops, it breaks way too many hydrogen bonds in our proteins. Our proteins fall apart. And we can die. Because our proteins denature so much, it kills us. So remember, I told you that if a good pH is 7.4 and we drop down to 7.2, we're very sick. If we drop down to 6.8, we're dead. What happened? What killed us? What killed us? Lemonade, that's right. Too much hydrogen. So the hydrogen, all that extra hydrogen ions, causes hydrogen bonds to break. That drop in pH causes hydrogen bonds in the protein to break. The protein falls apart. Now, by the way, I have a question for you. Really, truly, I'd like to see a raise of hands. How many of you in here were forced to take this class? Somebody made you take this class. You had to take it. Okay, I was just wondering. So I'm really, truly wondering why I see so many faces that make it look like I forced you to take this class. I'm serious. I'm really serious. I've never seen so many faces in a class that looks like I'm your high school teacher and I made you be here. Because I ain't. Okay? I'd rather die than be your high school teacher. Which also means you don't have to be here. You don't want to come? That's okay with me. But I thought, maybe I was wrong, but I thought on the first day we kind of talked about the fact that you actually wanted to be here because you actually wanted to go into the medical field and you actually wanted to help people. Was I wrong about that? Because I kind of sort of thought most of you were here for that. And I'm going to tell you, you may not actually realize this yet, but you have to know this stuff. You cannot heal people unless you know how their body works. When you give them drugs to help them, okay, are you actually going to know if the drug works or not? You can't know if the drug works or not because like some drugs break hydrogen bonds and make the body acidic. Should you give too much of that to your patient? And if you give too much to your patient, what will it do to them? Yeah. Okay, let me give you an example of why you should actually listen to this stuff, even though right now you might think this is crap and somebody's forcing you to learn this. So I have a granddaughter, okay, true story. She's 7 years old. And I have a few more years of education than the majority of doctors in the hospital, okay, just a few more years. I have 2 master's degrees, I have 2 undergraduate degrees, and I have a PhD. And my PhD alone took me 8 years to get through. Most doctors take 4 years to go to undergraduate, 4 years to go to medical school, they're done. Okay? I've been in school for over 12 years. Okay, that's a little bit more than most of your doctors, and then I've done a lot of other stuff too. So, my granddaughter is not feeling well. She's having some very unusual symptoms. My daughter, her mom, takes her to the hospital to have her checked. And I say to her, make sure the doctor takes this particular test, because I believe I know what's wrong with her. Do you know what the doctor says? I refuse. I refuse to take that test. That's what the doctor tells her. I refuse to take that test. So my daughter, of course being my daughter, says, why? What's it to you? I'm paying for it. Why won't you give her the test? She doesn't need it. How do you know she doesn't need it? Because you haven't given her the test. Well, I don't see that she has any symptoms. Well, that's because she's just sitting in your office and I'm telling you what her symptoms are. This doctor literally could not understand why my granddaughter needed this particular test. She didn't even understand. Well, here's what the test was. The test was to test for an antibody floating around in her bloodstream. Because I believe, and I know I'm right, that this antibody is being produced in her system when it shouldn't be. And what this antibody is doing is it is attacking her thyroid and causing her to have weird symptoms, like she's 7 years old and her hair is falling out. Okay? When she eats far too much. And then when she's done eating, she's starving, which means that her metabolism isn't working correctly. And she has a whole host of other symptoms that would lead me to believe that she's making an antibody she should not be making. Now, how do I know this? I mean, I did go to medical school, but I'm not a medical doctor. And so how would I know this? Well, I know how the physiology of the body works. And so I can think about what could be causing this problem because I know how the healthy body works. And I can figure this all out. So this doctor refused to take it, so I took her to my doctor. And my doctor took the test, and sure enough, guess what? I was right. Now she's 7 years old, and the good thing is, because we caught it early, by changing diet and a few other things, we can reverse the problem. But if I didn't know any better, her doctor just said, no, she doesn't need the test. And I would be dumb and not know and not say, get the test done. And what would happen? She would grow up and have a permanent disease. That's a problem, okay? Wouldn't it be better if you knew how the regular human body is supposed to work? Even though this may seem really boring to you, this was happening to her. Exactly what we're talking about today. Her proteins were falling out. Why? You have to know how they are healthy-wise before you can figure out why they're falling out. What are they made up of? How are they made? What are they doing in the body? If you don't know all that, you can't figure out the disease. And now you, because you were bored in this class, made my granddaughter sick with an autoimmune disease that she will have for the rest of her life because you didn't understand it. Because you didn't understand proteins. See how important it is? I know it may seem very boring to you, but you're the one who wants to go in the medical field, not me. I'm teaching. I don't want to go there. I quit going to medicine. It's like I had to help people. Ugh. Wipe their butts and their noses. I don't really care about people very much. And I don't care. If you want to be bored in my class, that's fine. I'm okay with that. If you don't even want to come to my class, I'm fine with that too, because I get paid whether you're here or not. Woohoo! I like this job. Okay, but here's the important thing. I'm going to be really pissed off if you're my granddaughter's doctor. I'm going to be really pissed off. And by the way, Moi is going to be taking a trip to Kaiser and having a little talk with that pediatrician too. You would not want to be her. And we're going to explain why she should have taken this test and what she could have possibly done to this child because she didn't take it. That's just wrong. So even though you may think this is boring, really what you're doing is you are not studying this information and you are potentially putting somebody's life into danger. That's how important it really is. Believe it or not. I had a student who was taking microbiology, and they teach you some funky diseases, stuff that we don't usually see in the United States. And this student, I remember her, and she used to complain, I don't want to learn this stuff. Why do I need to learn it? I'm never going to see it in the hospital. And you know what? She decided that she was going to do Doctors Without Borders. And she ended up in Morocco. She Facebooked me and said, you know what? They got a lot of funky diseases here. It's a good thing I learned these in microbiology. You never know. You never know. So if this is the job you actually want to do, you need to be a little excited about it. Because this ain't high school anymore, folks. Okay? You are not told you have to be here by your mommy or daddy or the U.S. government. You can go home, and the rest of us can have a good time. We're really clouded in here. I'm okay if you want to go home. If some of you just want to be a mechanic, that's fine. But if the rest of you want to work on the human body, you need to buck up. Okay? Because this is really important. And my grandkids are at stake here. And I don't like it when you're acting like this is boring to you. I want to see you going, oh my gosh, let me learn every little teeny tiny detail. Because I might not get it right when Dr. Harvey's grandkid is in and I know she's going to kill me. Right? Would you want to be that doctor I'm going to go talk to next week? I don't think so. It's going to be fun for me, but not for her. All right, let's take a break. It's for 3:55. Let's take 20 minutes. Come on back. Get some caffeine. Dunk your head in water. Wake up. Let's go.
I have a question pertaining to this. If temperature levels were to drop like a cold, do you make sure the protein as well?
No. Okay, so let's get started again. We've been talking about ways to denature proteins or to change the shape of proteins. And I told you if the pH drops, then it will break so many hydrogen bonds, the protein just falls apart. Another thing, this is why having a fever is bad, because fevers can also break hydrogen bonds and cause proteins to fall apart or to denature. And if the fever gets high enough, it can kill us. So for instance, if we have a fever of 104 degrees Fahrenheit or above, this is when proteins start to denature. They start to fall apart, which is why it's really bad to have a fever that high. Now here's a weird thing. Little kids, usually 10 and under, they seem to have a bit of a protective mechanism that nobody quite understands, where they can actually get a fever all the way up to 106 before their proteins start to fall apart and denature. But if a child has a fever of 106, you're going to be putting that child into ice, okay, to get that fever down. But for us, we only have to go to 104 before that fever starts to denature proteins. And literally, it can fry things in the brain. It can cause proteins to fall and to fall apart. So if I take an egg and I fry an egg in a frying pan, it changes shape, right? It looks totally different after I fry it. That's because I took that egg, which is mainly protein, and I increased the temperature, and I denatured those proteins, and I caused the egg to change shape. Why is it really bad to eat raw eggs? Because the eggs you buy at the grocery store typically have a bacteria in it called salmonella. Now, here's the weird thing. If you got an egg right from under a chicken's butt, that egg would not have salmonella in it. You could eat it raw. Which is weird because chickens, they're nasty creatures. They like lay their eggs in all their poop and dirt and feathers and everything. So you would think that egg would get salmonella in it. But if it did, could a chick grow in that egg? No, it would die because it's got bacteria in it already. So when a chicken lays an egg, it actually lays it with this waxy coating on it that even if the egg falls in poop, the bacteria can't get through that waxy coating. But now the reason it's in the eggs at the grocery store is because, like, I have a farm, so I go out, I get an egg from under my chicken's butt, and I take it in the house and set it on the counter and don't even put it in the refrigerator, and it'll stay there a month or two, and the egg is still good. But the eggs you buy at the grocery store, because you don't want to buy eggs that have, like, poop on it, because when I go to eat an egg, I wash it off and, you know, crack it, and there you go. They take those eggs before you get them at the grocery store and they throw them in chlorine bleach. And that bleach takes off the outer coating, and it also makes the eggshell porous so that any old bacteria can get into that egg now. And then on top of it, those eggs are, for the most part, about a year old by the time you buy them. That's why if you eat a fresh egg and you eat an egg from a grocery store, they don't taste anything alike because your eggs are super duper old. Mine are still like warm out of a chicken's butt. Way better. They taste very different. So, but when I cook it, I've raised the temperature And I'm denaturing proteins in that bacteria too, so I won't get sick from that bacteria. I've killed the bacteria by cooking it as well and denaturing all of its proteins. Now sometimes I don't want to denature proteins, I don't want to break them apart, I just want them to change shape. Now how do I trigger this protein to do the shape change? Well, there is a chemical that I can add to a protein, which is the PO4 thing I showed you before. This chemical is called phosphate. If I add a phosphate to it, it breaks a few hydrogen bonds and I get a protein that changes shape. What if I wanted to develop a drug? And this drug needed to make particular proteins change shape. What chemical would you recommend I put in this drug? Phosphate. It'd be kind of dumb not to have phosphate in the drug if I wanted to make a protein change shape. I need to add a phosphate. Now, in our body, we have all kinds of phosphates, and those phosphates come from this chemical right there. See this right here? Here's a phosphate right here. Here's a phosphate here. Here's a phosphate here. Now, this chemical is made up of this thing right here. This is called adenine. This right here, this is a ribose sugar, and it has 3 phosphates attached, or what we call triphosphate. This chemical that I'm showing you on the board is called ATP. This is adenosine triphosphate. This is a very important chemical. This is the chemical that carries all these phosphates so that we can have a whole bunch of shape changes of proteins in our body. What would happen to the beating of your heart if we had no more ATP molecules in the body? It would stop. That's kind of an important chemical. So kind of sort of have to have this. Now, by the way, we're going to talk about this more next week, but in order to make ATP, I have to eat carbohydrates, I have to eat fats, and I have to eat proteins. And these are my major sources to be able to make this ATP molecule, which makes all kinds of proteins change shape in my body all the time. My brain, made up of tons of proteins, they need to change shape all the time. If I don't have enough ATP, my proteins don't change shape in my brain stops, I'm dead. So that's why if you like totally fast for 40, 50, 60 days, you're going to die. Not gonna last. Matter of fact, what's the longest amount of time you can fast? 100% not eating anything, not drinking any juice, just water, before the body says, I don't have any more ATP.
Is 30 days? It's after
40.
2 weeks.
40 days. You can fast for 40 days. You have to drink water. You can fast for 40 days, but people have tried to go past 40 days. Day 41, dead. It seems that we have enough of an ATP supply to get us to day 40, typically, but not to day 41. Weird. So this is just a picture of a typical protein, and hydrogen bonds are breaking, you get one shape. Hydrogen bonds reattach, you get another shape. This happens in our body all the time. Now, here's a super important thing that you need to know. There are certain kinds of proteins in our body called enzymes. Enzymes are always globular proteins. So they're that glob shape. Are globular proteins primary, secondary, tertiary, or quaternary? Tertiary. If I put 4 globs together, what shape do I have? Primary, secondary, tertiary, quaternary? Quaternary. What is the only protein in our body that is quaternary? Hemoglobin. Very good. Now, these enzymes are globular. They're tertiary. They're globs of protein, and they act like a catalyst. Now, a catalyst is very important if you haven't had chemistry. A catalyst in the human body is an enzyme that makes a chemical reaction go a lot faster. Okay, so I'll give you an example. Let's pretend that I'm going to build this box, okay? And I'm going to put this box on the table, and I'm going to make this box out of glass so we can see inside the box. Now, here's a couple things you got to know about my box, okay? There's nothing inside my box. There's no air. There's no molecules. Nothing. My box is totally empty. And my box can't vibrate. You can't move my box. My box doesn't get hotter. It doesn't get colder. It just stays at room temperature. Okay? You with me so far? Now, here's what I'm going to do. I'm going to put inside my box these two molecules that I know have the ability to attach and bond to each other. Okay? But here's what I'm going to do. I'm going to put these two molecules 1 centimeter apart in my box. Now that's about ½ inch. Okay? So I'm going to put them about ½ inch, 1 centimeter apart in my box. Just going to place them right there. Now, every single atom, every single molecule in the world has what we call kinetic energy. This is in every single atom, every single molecule. Now what this kinetic energy does is it makes these atoms, it makes these molecules vibrate. They're constantly vibrating. Remind me like somebody who's on speed. You know, constantly vibrating. See, my morning class didn't get that either. I just do not understand. You people are not ghetto enough. I don't get it. You live in the high desert. Do you not know that the high desert is the methamphetamine capital of the world? We produce more speed in the high desert than any place in the entire world. This is something to be proud of. No.
I used to live across from a meth lab and it exploded. I didn't know.
So it's like my next door neighbors sell meth, so I believe it.
My students this morning did not even know about Christmas lights. Y'all know about Christmas lights in July, right? Your neighbor's Christmas lights go on, it means they're done cooking. It's time for all their friends to come and buy. Did you not know this?
No.
Why do you think people in the high desert turn Christmas lights on and off throughout the year and it's not Christmas? You think they just forgot and flipped a switch? I don't think so. Okay? I live in Lucerne Valley, okay? There are lots of methamphetamine labs out there. Go kaboom all the time. And I have a neighbor who is the top producing methamphetamine lab in the high desert. I know, because the FBI, DEA, all kinds of people have been there all the time. He comes and goes, you know, in and out, prison, that kind of thing. And his sister just blew up the other day.
What the hell?
Up.
His sister blew up.
Probably at least 500 feet in the sky. Okay. I mean, you could see the smoke from everywhere. It's pretty amazing. But we know when he's home because the Christmas lights go on. And then there's lots of traffic. And then the Christmas lights go off and he sold everything. You people don't know this?
No.
Do you know about the shoes over the wires?
Yeah, that one.
Excellent. We're at least getting somewhere. Okay?
I'm like, wait, what are you saying?
He knows how to buy.
I was wondering about the shoes on the wire. Come on, somebody tell Joseph what's the shoe on the wire mean? They're selling drugs. Same thing. You tie it together up on the wire.
That explains how many neighbors have Christmas lights up there.
So in our methamphetamine people, literally, we're not talking Magic Mike. It makes me drool. I can't talk while I'm drooling, okay? So anyway, I never even saw the movie, so I don't know. I'm just joking. Who plays Thor? Yes.
I know you
Yes.
talked about that.
Now, if we're talking about him, I will drool. Okay. She knows his name. So our methamphetamine addicts, one of the things that that drug does to them literally is it actually makes their enzymes even faster than normal. So that they really do move fast, which is why they call it speed. And their whole body, their whole metabolism speeds up. Which, by the way, when you're working in hospitals and you have a methamphetamine addict come in, one of the problems is telling how old they are. Because usually their metabolism has sped up so fast that they also age very quickly. And you will be surprised when you have this methamphetamine addict come in and you think he or she is like 60 years old and they're only 28. So what it's doing is it's affecting enzymes. It's affecting this catalyst. Now, let's go back to my two molecules in the box. I've put them about 1 inch apart and they have this internal kinetic energy that makes them vibrate, okay? Now, wild guess. How long do you think it'll be at 1, or actually it's about a 1/2 inch. They're a 1/2 inch apart and they're vibrating. How long do you think it'll take them before they vibrate close enough together they can bond to each other? Wild guess. I don't care. You don't have to be right. Wild guess. How long do you think it will take?
30 seconds.
30 seconds. That is so far too fast. Wild guess.
1 second.
No, that's even way faster than 30. Wild guess. How long do you think it'll take? 20 minutes. Okay, still far too fast. How long do you think it'll take? A day. Still way too fast. How long?
3 years.
3 years. We're getting closer. How long?
20 years.
Too slow. 10. On their own, if they were just vibrating, it would take them about 10 stinking years for them to finally get together when they're only a 1/2 inch apart. Now imagine if chemicals are inside of our cell and it took them 10 years to bond to each other and have some kind of chemical reaction. By then, we're dead. Because most of the chemical reactions inside our cells are happening in microseconds. Really super duper fast. Now the only reason they're happening so fast is because of these enzymes. So we need to talk about how do these enzymes work, how do they speed up, make these chemical reactions happen. So basically what happens is an enzyme will grab that first chemical I put in my box and also grab the second chemical I put in my box and slap them together really fast and then let them go. So that inside our cell you have enzymes that are grabbing these chemicals, slapping them together, and now you've formed a new product. So if you could pretend like my two hands are an enzyme. I have like a little pocket in the palm of my hand here, and a little pocket in the palm of my hand here. And my little pockets are like magnets. They can attract chemicals in the cell. So let's say chemical A is attracted into this pocket here. And then chemical C is attracted into this pocket here. Now the job of the enzyme is to pull those chemicals in like a magnet, and once it has them in, slaps them together. And then lets them go as a new product. It's made something new. If we just let those chemical A and chemical C float on their own in the cell, they may never find each other. They may never bond, or they may take 10 years to bond, and we need them to bond now. So if you look at it like this, let's say that this is my enzyme, okay? This is my glob of protein, and here's one of my pockets, here's the second pocket, okay? So I got one pocket here, let's say this is pocket A, and I got another one here, this is B, okay? And then I have all these chemicals, C, D, X, Y, L, they're all floating around in the cell. This pocket right here will attract one particular chemical. Let's say it attracts X into the pocket. The second pocket is going to attract a different chemical in, and let's say it attracts chemical D. Now, you need to know that these chemicals that are attracted into the pocket, we actually refer to these as substrates. So you have substrate X, you have substrate D. Okay? And the pockets are really called an active site. So you have active site A, you have active site B. So active site A has attracted substrate X. Active site B has attracted substrate D. Are you with me so far?
Yes.
Okay. Now, what we need to happen is we need this enzyme, this protein, to come together. Slap these two substrates together. How do we get proteins to change shape? How does a protein change shape? Add a phosphate. So, we're going to add a phosphate. Once we add a phosphate, our protein is going to change shape. And it'll allow substrate X and substrate D to come together and bond. You have now formed a product. That'll go floating out in our cell. Now here's the other cool thing. Our enzyme is going to go back to its original shape. And enzymes can be reused. You can use them over and over and over again, and it'll pull substrate X and substrate D back into the active site. And you'll do the same thing over and over and over. Each different enzyme pulls in a different substrate, makes a different product. So we have a lot of different enzymes in our body. And we're going to do a lab, I think we're doing it this week, where we're going to test enzymes. And we're going to try to ruin or destroy the enzymes. And how would we destroy an enzyme? It's a protein. How would you suggest I destroy this protein? Microwave it. Yes, I could make it really hot. What else could I do to my protein to destroy it?
Add an acid.
Add an acid. Now, somebody said what over here? Freeze it. Freeze it. I'm glad you brought that up. Can I freeze a protein and destroy it? And the answer is actually no. Because here's what happens when I freeze a protein. It hardens. Think of an enzyme kind of like clay. You know, when clay is nice and warm, you can move it around, change different shapes. But if I freeze the clay, it hardens, right? Now, if I defrost that clay nice and slow, warm it up nice and slow, can I mold it around again? Yeah. Same thing happens with enzymes. If I freeze an enzyme, it'll harden. But if I warm it up nice and slow, it'll go back to working again. So I don't actually destroy it, but I can stop it by freezing it. As long as I warm it up nice and slow. Now, what would happen if I warm my enzyme up too fast? What do you think would happen? If it's frozen and I warm it up too fast, what would happen? What would happen to clay if I warm it up too fast? Cracks. Enzymes crack too. So what if I have this scenario, true scenario? I had a friend, and then well, no, not yet. I'll let you go in a couple minutes. But I had a friend a couple years ago who decided he was going to go mountain climbing. He was very much not prepared. He went mountain climbing in May. He went climbing Mount Whitney, which is a pretty tall mountain. And May is usually a nice month. But it decided to snow in May this year that he went climbing. Now, he went climbing in shorts. He didn't bring anything with him. All he had for food were M&Ms, and he had a very small bottle of water. Not smart. So number one, it snows when he didn't think it was going to. Number two, he's not prepared. He shouldn't have been doing it. But he survives. He actually lives on the side of the mountain all night long in the snowstorm and is alive the next morning. But he is very frozen. And two other mountain climbers find him. And they climb up, they find him, and they bring him back down. Now, he's very frozen. What would you suggest they do to warm him up and keep him alive?
Put a blanket on.
Put a blanket on him. Now, here's the problem. If I put a blanket on somebody who's super duper cold, is there any way they can generate heat under that blanket? No, that's the problem. Yes, putting a blanket on him, but all that blanket does is keep the cold in him. So how do I warm him up?
Body heat. Take off your clothes. Body heat.
So you want me to get naked and get naked with him? You're absolutely right. That would be the best way to do it. Now, they're in the middle of nowhere, so I can't use a blow dryer. But even with a blow dryer, but think about it, even with a blow dryer, would that not heat him up too quickly? What would you recommend that I make hot chocolate and make him drink it? No, that is a very bad idea. Which is exactly what those guys did who found him. Because they said, I'm not getting naked with any guy. I'm not gay. That's what they said. So instead what they did is they made a bunch of hot chocolate and poured it down his throat. Now imagine those enzymes, all in his body, frozen. And now I pour hot chocolate over these frozen enzymes. What happens to them? They crack. And that's exactly what happened to him. His enzymes cracked. He went into all kinds of seizures. He had all kinds of brain damage. And within 30 minutes, he died. Now, if they had gotten naked with him and given him body heat under blankets and warmed him up slowly, he would probably still be alive to this day. But instead, at the age of 22, he died because somebody was afraid to get naked with somebody who, by the way, was completely unconscious and would have never known. So this is really important. Now let me tell you one other scenario. True story. There's a 12-year-old little boy, and he is fishing with his dad. Now they're ice fishing, so they're on this ice lake. They dig this, saw this hole in the middle of the lake, and they're fishing. And the little kid is not paying attention, okay, like little kids do, and he falls in the hole. Now, when you fall in a hole on an ice lake, you don't just bob right back up through that hole. You fall in that hole, and the lake takes you underneath this slab of ice. So they can see him, luckily, under this ice, and they're following him as the water is taking him down. And somehow they are able to get him out of that water. 66 minutes later. He has been underwater in this ice lake for 66 minutes. Now, very luckily for this little boy, his dad was also a doctor. So his dad got naked with him and began warming him up. Didn't give him CPR yet. But when he began to get warm, then gave him CPR. Brought the boy back to life almost 70 minutes later with 0 brain damage. Why? Why was there 0 brain damage?
No.
He hadn't been breathing for an hour and 10 minutes.
Because when your body gets cold, it slows itself down to protect itself.
It. What is it that is slowing down? What have we been talking about?
Metabolism.
The enzymes, right? So when the enzymes freeze, what they're doing is normally they're doing chemical reactions, right? And when they freeze, no more chemical reactions, no more metabolism. Now, by the way, one other thing you have to know. With every single chemical reaction we have, there's always a waste product. And those waste products are almost always acidic. Okay, so follow me with this. So his enzymes freeze. He has no chemical reactions really happening. So that means he has no waste products. So there's no acids being made. Does his pH change? No. But what if he had fallen into a warm lake and was underwater for 66 minutes? He would have died, wouldn't he? Because his enzymes would still be moving, and he would be making all kinds of waste products, lots of acids that he can't exhale. By the way, we exhale a lot of those waste products. Because he's not breathing, he can't exhale them. So his enzymes are still moving because he's warm, and he's making waste products which are acidic, and when you make acid, your pH goes down, which denatures proteins all throughout the body, and you're going to have damage even if we bring you back to life. But because he was frozen, his enzymes stopped. No waste products, no acids, no pH change, no damage to his proteins. So, okay, let me ask you this question. Theoretically, kind of, sort of, do you think it's possible that we could actually freeze a person so well that we stopped every single one of their enzymes from moving, every single one, could we freeze them and bring them back to life in 100 years with no damage? He says yes. Anybody else say yes? We freeze every single enzyme, so there's no chemical reactions happening. Zero. None. Could we freeze them and bring them back to life without any damage? Think about it before you say no. I know it's crazy, but could it possibly be done if we could learn how to freeze every single enzyme?
Technically. If we went
Technically.
Theoretically.
Exactly. Not saying it can be done yet, but they are trying, by the way.